Hello everyone. This session covers the review of AC single phase circuits. To start with, a simple RLC circuit is considered. This is a coil of resistance 2.5 ohms and inductance of 60 millihenries. And this coil is connected in series with a capacitor of 6.8 microfarads, and the set is connected to 230 volts 50 hertz AC supply. Now the aim of this problem is to determine current drawn from the supply, right? So here to find the impedance, you need to find the impedance of the elements first, because the supply frequency is 50 hertz. Impedance of these two elements is to be obtained. Impedance of this is j omega L, and impedance of this is minus j by 2 pi fc. So from this, jxl and minus jxc values are computed, and the net impedance of the circuit is written. So which is equal to R plus jxl minus jxc. And once the net impedance is computed, the current through the circuit can be calculated directly from I is V by Z. So this is a phasor, and I is 0.512 at an angle of 89.52. The current therefore leads the voltage as expected in a predominantly capacitive circuit. The circuit is called as a predominantly capacitive circuit because when you see here the value of the inductive reactance, it is 18.85 ohms, and the value of capacitive reactance is 468 ohms. So this is predominantly called as a capacitive circuit. That's why you got the value of the current as the leading value when compared to the voltage. Now here another problem that is given is to determine magnitude and phase angle of the current drawn from the supply in the circuit. So here a simple RL parallel circuit is given, and which is connected to a single phase AC source of 20 volts and 50 hertz. Here also the value of inductance is given in terms of millihenries, which is to be converted in terms of either impedance or admittance. Actually, this problem can be solved in two ways. One is because it is a parallel circuit, admittances of two elements are computed, and those admittances are added, so that net admittance you will get for this circuit, and from that you find the current in this current drawn by the elements. Or we can find the impedance of the net circuit like R in parallel with JXL, like this, and from this we can find the current is I is V by Z. Or else we have to use, when we write admittance, we have to use I is Vy. So that's why two procedures are given here. This is solved by means of admittance, and this is solved by means of the impedance. Here we can have a small attempt to draw phasor diagram of this circuit, because I is equal to the phasor addition of IR and IL. So IR is like this, and IL is like this. The net current through the circuit is IR bar plus IL bar, which lags behind the voltage by some phase angle phi or theta, whatever we call. So here this phase angle is 38.7 degrees. Because it is a RL circuit, it's understood that current is lagging behind the voltage phasor. Now, when we look into RC circuit, the problem is very similar one, but here instead of the inductance, here capacitance is given. So as discussed previously, this also can be solved by means of the impedance or by means of the admittance. When it is to be solved by means of admittance, admittance of this element is 1 by 5, and admittance of this element is J 2 pi fc. Then the net admittance is equal to G plus BC, which is 1 by 5 for this, and for this it is J2 by FC, which is J25 ohms. Net admittance is 0.2 plus J0.25 Siemens, and when voltage is equal to 24 at an angle 0, then the current is I is V into Y. So this indicates that current leads the voltage as it is to be expected in the capacitive circuit. In the alternative way, we can solve this by taking R in parallel with 1 by J 2 by Fc, because 1 by J 2 by Fc or minus J by 2 by Fc is reactance of this Xc. So Z is parallel combination of these two and I is V by Z. So both the values are same. Just observe here in the previous problem, frequency of the system was 50 Hz and here frequency of the system is uh, 50 Hz and here frequency of the system is 4 kilohertz. So when you attempt to draw a phasor diagram for this system, which is equal to voltage is in phase with IR, that is current through the resistor, and IC leads the current by 90 degrees, and the net current is IR plus IC is the net current which leads by some angle phi. In this case, this angle is 51.34 degrees. Okay, now we will see, or we will take up another problem, which is the combination of RL and C elements. Here it is R in series with the inductive reactance, it is J10, and here it is capacitive reactance. It should be taken as minus J20. So the net impedance of the circuit can be computed as 5 plus J10 in parallel with minus J20, and from that the total current drawn from the supply can be obtained, and then from that phase angle of the inductive branch and the circuit of the phase angle of the entire circuit as a whole can be obtained. So this can be solved by IL can be directly computed by V by ZL, and here only magnitude is written. When you want to write the phase angle also, then simply you can write V 100 at an angle 0 by this ZL. You can write the phase angle of this, and from that you can find the value of the total phasor current, and then from that you can find the magnitude, and the total current drawn magnitude is 4.96. And then inductive, the second bit that is to be found is phase angle of the inductive branch of the circuit. That means this phase angle 5 plus J10 phase angle is to be obtained, and then as a circuit as a whole the phase angle is to be obtained. So for this 5 and plus J10, the phase angle is tan inverse 10 by 5, 63.4, and for this entire thing, after computing the entire impedance, we can find the phase angle of the circuit. And to just give the review of the power components, we know that complex power is S is equal to P plus JQ, and when the power factor angle is leading, it is positive. When power factor is lagging, S is P minus JQ. So here it is a simple diagram which is with the lagging current. When V is taken here and I cos phi is in phase with V, I sin phi is in quadrature with V, and vectorial addition of I cos phi and I sin phi will give you I. Square root of I square cos phi square plus I square sin phi square is equal to I, which lags behind the voltage by phi angle. This phi is convention is also sometimes taken as theta and sometimes it is taken as phi. So when you want to write the power triangle, multiply this with I cos phi and multiply voltage with I sin phi, Vi cos phi and Vi sin phi, and vectorial addition of these two is V into I. This Vi cos phi is called as the real power, which is represented in watts. Vi sin phi is called as reactive power, which is represented in vars, volt ampere reactives, and Vi is the apparent power, which is represented in volt amperes. And power factor of the circuit is actually can be computed by in multiple ways. Actually, we define the power factor is cosine of the phase angle between voltage and the current. So phase angle between voltage and current is the phase angle phi. Cosine of this is cos phi is the power factor, and the same cos phi is also defined as the ratio of the real power to the apparent power, that is P by S, or P is S into cos phi, because we write S is equal to P plus JQ, and which is equal to P is S cos phi and Q is S sin phi. Okay, so another small problem can be taken up at this stage. So on power and power factors of the circuit, two impedances Z1 and Z2 are in series and pass an effective current of 5 amperes. Determine active power, reactive power, and apparent power, and also power factor of the circuit. Z1 and Z2 are given because they both are in series. The effective impedance of the circuit is Z1 plus Z2. Power factor is R by Z, which is 0.855. Active power is VI cos theta, which is magnitude of I square into R, because effective current through the circuit is given, that is magnitude of the current is given I square into R inwards. Apparent power is I square Z. Reactive power is I square into XL. When voltage is known to us, directly we can compute S by means of V into I conjugate, and real part of S will give you real power, reactive part of that S will give you the reactive power. For the circuit shown in figure, you are asked to determine the value of the impedance if the source delivers a power of 200 watts and there is a lagging power factor of 0.707. Also find the apparent power. Here voltage is given in terms of time domain representation, that is V is represented in terms of Vm into sine omega t plus theta or phi. So here RMS value is 25 by root 2. Frequency of the system is omega, and here it is this source voltage is to be taken as 25 by root 2 at an angle of 25 degrees. 25 by root 2 is 17.68 at an angle 25 is the representation of this source in phasor domain. Here value of determine the value of the impedance if source delivers a power of 200 watts and lagging power factor of 0.707. That is, power factor angle is 0.707. So total resistance of the circuit is known as R, and this total impedance of the circuit is Z. If we assume, then R cos theta is R by Z, which is 0.707, and the relation between R and Z can be obtained here, and active power of the circuit is given as 200 watts, where V is magnitude of V is known to us, magnitude of I is not known, and cos theta is known to us as 0.707. From this, magnitude of I can be computed. So total magnitude of the total impedance can be computed, and from that ZT, this small r is to be subtracted because ZT is total Z plus R. And apparent power is V into I. Here it is magnitude is only taken when you want to calculate P plus JQ in phasor form. This V bar and I bar can be written here so that this computation can be done vectorially also. When another problem is similar problem is taken up here. In the parallel circuit shown in figure, power in 5 ohm resistor is written as 600 watts, and total circuit takes 3000 volt amperes at a leading power factor of 0.707, and you are asked to find the value of the unknown impedance Z. Total impedance of the circuit is 5 plus J5 in parallel with Z. So from that, the value of these computations can be made here, and total value of the impedance can be obtained.